Okay, here's some ways to think about these ramp questions. So if we have just a simple situation like this, where we have a block and it's at rest on a ramp, so it's in equilibrium, and maybe this is the maximum angle that we can tip this ramp up to before this starts to slide. So this is the force of the maximum force of friction that we can get. Okay, so at this angle the friction is just balancing out the gravitational pull. So these are the three forces acting on the object. Gravity's pulling it straight down. It's sitting on the surface of the ramp, so that's pushing straight up on it. And friction is opposing its attempted motion, which would be to slide down the ramp. So if it's in equilibrium, then all these forces will be balanced. Okay, so the sum of all the forces will equal 0. So often on these ramp questions we sort of want to break it down into which forces are acting along the ramp, which we might call the x direction, and which ones are going perpendicular to the ramp, which we could call the y direction. But I just want to show you how we can solve this problem without breaking the forces down. So we know that the sum of all the forces is 0, so let's just add them tip to tail. So we're going to we've got a gravity force acting straight down, then we've got a frictional force acting straight along the ramp, and then we've got a normal force that's completely perpendicular to the ramp. So you can see that the frictional force and the normal force are going to be perpendicular. And all three forces have to add to 0, which means tip to tail, they just make a closed triangle. Okay, so this is awesome. Not only is it a closed triangle, it's a right angle triangle. So all we need is an angle in here, and then we can figure out the relationship between all three. So if we know this angle here, we want to translate it into our triangle. So if we extend this down a bit, we can see this is 90. Okay, so whatever theta max is, theta max plus this angle, let's call it beta, these have to add to 90. But this side of our triangle right here, the FN side, is perpendicular. So beta and this angle also must add to 90. So that means that this angle right here is theta max. Just in case. Okay, so let's just put in some numbers to make this clear. So for example, if theta max were 30 degrees, then theta max plus this angle must be 90, so that means this must be 60. But now this angle plus this angle must be 90, so this must be 30. So whatever angle shows up here, we'll see the same angle here in this top corner of our triangle. So theta sits right here in this triangle. So then, if this is in equilibrium, this is the maximum angle, maybe, then we can figure out the coefficient of friction, because FF would be equal to mu Fn. And if that's theta, then this is the opposite, and that is the adjacent. So tan theta is equal to opposite, which is mu Fn, over adjacent, which is Fn, and we get that the tan of the angle is equal to the coefficient of friction. A very cool and elegant result.